Now let's write down the alternative epsilon delta characterization of limit. This may or may not be more familiar to you from your previous calculus classes. I should mention that I'm doing a few things in a different order from your book. So your book refers to what we're about to write down as definition 2.1.1, and then the sequences characterization of limit is their proposition 2.1.2. And as long as you get the numbers right on your homework or exams, I won't worry too much about whether you're calling it a definition or a proposition. So let's let X be a domain in the real numbers. Let's let F be a function whose domain is X. And we're going to let A limit point of X, and then we're going to let L be a real number. So this is the characterization of limits at limit points. The special case for isolated points is the same as before. Then the limit as x approaches A of f of x equals L. That means both it exists and it's L in particular. If and only if for all positive numbers epsilon, there exists a positive number delta such that if x minus a, the distance from x to a is less than delta, and we also need x to not equal a, and we can indicate that very concisely by putting a 0 less than absolute value of x minus a less than delta, so that if that is true, then the distance from f of x to L is less than epsilon. And you have you may have seen something like this in your previous calculus classes, but you might also notice, hey, this looks an awful lot like the epsilon delta characterization of continuous functions of theorem 1.7.5, and we can write out a proof that's very similar to the proof of theorem 1.7.5, or another thing we can do is we can try to come up with a short circuit, try to come up with a way to prove this using theorem 1.7.5 to do all the heavy work. So here's how we're going to do this. We're going to let g be the following function. G of x, it's the same thing as f of x, as long as x is not equal to a. So we said a was a limit point. A might be a point that's in x or a point in the closure of x. It doesn't matter too much which. And then we're going to say that g of a is equal to L. And then g is a function whose domain is x union a, and whose range, again, is the real numbers. And now let's look at a few things we know. By corollary 2.1.3, that was the last thing we proved in the last video. We have that the limit as x approaches a of g of x, that limit is equal to L if and only if G is continuous at A. Then by our definition of limit, we have that the limit as x approaches A of g of x equals L. That is true if and only if the limit as x approaches A of f of x equals L. And since that's part of a different video, let's write out how this works. Let's let xn converge to A. Xn is in X but not in A. Then g of xn equals f of xn, since xn is not equal to A, so it's not the one point we've defined. So g of xn converges to L if and only if f of xn converges to L. So the limit as x goes to A, g of x equals L. That's true if and only if g of xn goes to L for every sequence of xn. And it's like this. If all the sequences of g of xn's converge to L, that's true if and only if all the sequences of f of xn's converge to L. And so we've got that, and so put it all together. Now, when is G continuous at A? So by theorem 1.7.5, G is continuous at A if and only if for all positive numbers epsilon, we have that there exists a positive number delta such that if x is in the domain of G and x minus A is less than delta, then G of x minus G of A, that is less than epsilon. That looks an awful lot like the condition in the theorem. We've got some differences. We've got G's instead of F's. So we've got we don't have the 0 less than x minus A. So, but we can go pretty clearly from here. So if G is continuous at A, then for all epsilon bigger than 0, there exists a delta bigger than 0 such that if x, so we know that something's true for all x in X or A in the domain of G, so certainly the same thing is true for all x except A. So if x is in X and x is not equal to A, and the only way x minus A can be 0 is if x equals A, then now g of x is not A by assumption, so g of x is f of x, and then g of A by definition is L. So there we've got the condition in the theorem. So if g is continuous at A, then we have the condition in the theorem. And conversely, if x is equal to A, then g of x is the same as g of A, so g of x minus g of A is less than epsilon for any epsilon greater than 0. So let's go ahead and give our for all epsilon greater than 0 statement a label. It's green. Let's call it green star so I don't have to keep writing it out. So if our green star condition is true, then we have that for all x in X union A with x minus A less than delta. So either x is not A and our green star condition gives us what we need, or x is equal to A and we always have what we need. So in either case, then g of x minus g of A, which is f of x minus L if x is not A, is 0 if x is A, is less than epsilon. So g is continuous at A. So put it all together, g is continuous at A if and only if our condition star from the proposition statement is true. So now let's do the last thing we need to do. We need to relate the limits of f and g. So let's suppose limit as x approaches A of f of x is equal to L. Then for all sequences in x minus A with xn converging to A, we have that f of xn converges to L, and that is by our definition in 2.1.2 by what we're using as the definition of limit. And then if xn is not equal to A, then g of xn equals f of xn. So we have that g of xn is also converging to L because it's the same sequence as f of xn. And this is true for all such sequences. So one way we say that is that our sequence was arbitrary. So the conclusion is that limit as x approaches a, f of x, g of x is also equal to L. And you can make exactly the same argument in reverse, just switch the roles of f and g. So similarly, if limit as x approaches a, g of x equals L, then the limit as x approaches a, f of x equals L. So let's put this all together. So limit as x approaches a, f of x equals L. That is true if and only if the limit as x approaches a, g of x equals L, and then because g of x, because g of a is L, this is true if and only if g is continuous at a, and that is true if and only if our complicated conditions, Green's, our epsilon delta condition is true. So all four of these things, limit it as x approaches a, f of x equals L, limit of g of x equals L, g is continuous at a, and condition with the epsilon deltas, they're all equivalent to each other, and that is precisely what we wanted to prove. Now I would like to tell you one interesting thing about uniformly continuous functions. This isn't in the book, but is sometimes an illustrative example. Let's let x be a bounded subset of the real numbers. And let's let f be a function whose domain is from x to the real numbers. And then here is part A of the proposition. I believe I will make this an exam study problem, and this is if f is not uniformly continuous, then there is at least one point A in the closure of X such that the limit as X approaches A of f of X does not exist. And then here is part B, and that's that if f is uniformly continuous, and A is in the closure of X, then the limit as X approaches A, f of X, does exist. So uniform continuity guarantees that there's a limit at every point in the closure, and continuity means there is a limit at every point in the set, and moreover the limit is in fact the value. But continuity on its own doesn't give you limits at other points in the closure. In fact, if you've got continuity but not uniform continuity, there's got to be somewhere where you fail to have a limit. At least if your domain is bounded. Unbounded domains can be a little weirder. Now let's cover a few standard theorems for limits. Here are some pretty standard results regarding the sum, product, and quotient of limits. So let's let X be a domain, A be a point in the closure of X, either a limit point or an isolated point. And we're going to let F and G be functions whose domain is X and range is R. And then let's suppose that the limit as X approaches A, f of X, and the limit as X approaches A, g of X. Let's suppose they both exist. We'll give them names. The limit of X, f of X is L, and the limit of g of X is K. And then the limit of the sum is the sum of the limits. The product of the sum, the limit of the products is always the product of the limits, and quotients, as usual, are a little trickier. All you have to do is make sure you're never zero. G of X is not equal to 0 for all X in X, and also the limit of the G's is not equal to 0. Then limit of the quotient is the quotient of the limits. And the proof of this is very straightforward and very boring, so I don't want to get into it. It's basically you just apply our sequence definition of limits. This is one of the reasons why I wanted to use the sequence definition as the definition instead of the epsilon delta thing, because all the good theorems from section that we know from section 1.3, they are all about sequences. So this proposition basically just falls out of proposition 1.3.6. What we're going to do now is we're going to talk about when infinite limits and limits in infinity. Basically, we're going to throw all the infinities into our definition, and we're going to see how that plays out. So here is definition 2.1.10. So as usual, let x be a set of the real numbers. A is a limit point of x, and f is a function from x to the real numbers. If a is an isolated point, then the limit as x approaches a of x is f of a, so that's not allowed to be infinity because we don't like to allow our functions to be infinity. But if a is a limit point, then the limit can be infinity. Then we say that limit as x approaches a f of x that equals positive infinity. Now you could define that in terms of sequences converging to a and f of those sequences going to infinity. That works fine, but I think in this case we're going to go ahead and follow the book and just use the epsilon delta, or rather the p delta characterization. So the limit is infinity if and only if, but definitions are always if and only if, for every number p, every real number p. This really matters for large positive values of p, like epsilon delta usually matters for small values of epsilon, but we're going to write it for every p in R. There is a positive number delta such that if x minus a is less than delta and x is not equal to a, then f of x is greater than p. So your limit is positive infinity if you can force f to be as big as you want by restricting yourself to be close to a. I think I will leave you to write out for yourself the precise, rigorous definition of the limit being negative infinity. Now let's go ahead and write down the definition of a limit at infinity. So here's how this works. Let's let x be a subset of the real numbers, and suppose x is not bounded above. So you can find points of x that are as big as you want. Let's let f of f be a function from the domain in x into the real numbers. And then let's let L be a real number. And then we say that the limit as x goes to infinity, f of x is equal to L. We say that is true if for every positive number epsilon, there is a real number R. I don't want to use the same P as before, such that if x is in x and x is bigger than R, and there's always going to be at least one x like this because your set x is not bounded above, and if there wasn't an x like this, then r would be an upper bound. Then, as usual, f of x minus L is less than epsilon. And some exercises which might show up on homework or exams would be to have you write out these definitions at minus infinity, or when would you say limit as x goes to infinity, f of x equals infinity, or to come up with definitions for these things in terms of sequences and to prove that they work. Proposition 2.1.5 works just fine for limits at infinity, but you have to be a little bit careful about limits that are infinity. So here we're going to write out proposition 2.1.11. This is the analog to proposition 2.1.5 for infinite limits. So we're going to let x be a subset of the real numbers, a be a point in the closure of x. Really, this only matters if a is a limit point and f and g are both functions whose domain is x and whose range is the real numbers. And then we're going to suppose that the limit as x goes to a of f of x is positive infinity, and the limit as x goes to a g of x is some number k, where k may or may not be infinity, it may or may not be positive. So then we've got the following things are true. So first off, if k is not negative infinity, if it is any finite number or positive infinity, then the limit as x goes to a, f of x plus g of x, that is positive infinity. Then there's part B, and that's that if k is positive, including positive infinity but not including 0, then limit as x goes to a, f of x times g of x is positive infinity. And part C is that if we still don't want to divide by 0, and k is a non-negative finite number, k being 0 is fine, then the quotient also is converging to infinity. And the proof of this is going to be left as an exercise. It's one of our usual theorems about sums and products and quotients that that they necessarily behave the way we want. And this one also works just fine if a is the point at infinity, if these are all limits as x goes to infinity, but writing that out is more trouble than it's worth. The last topic of section 2.1 and also of this video, we're going to talk about one-sided limits and maybe circle back a little bit to increasing functions. So here is a definition. This is sort of standard notation in analysis. Let's let x and y be sets, E is a subset of X, and F is a function from X to Y. Y might be the real numbers, might be some other numbers. Then F restricted to E is a function with domain E. And where we just write F restricted to E of X is the same thing as F of X. So this is just taking, taking all the points in E and keeping their values and taking all the points X that are outside of E and just forgetting about them, forgetting that we once defined F outside of E. So this is what's called a forgetful functor sometimes. But this can be useful if you've got a function you like and a domain you like, and the function just happens to be defined on too many places. You can just throw away the too many places. And that's very important in the next definition. So let's let X be a subset of the real numbers and F be a function from X to the real numbers and a point in the closure. And then we say that the limit as X approaches A from the left, we write that as A to the minus F of X. We're going to say this is the same thing as the limit as X approaches A, and then we'll take F restricted to the numbers below A. That function, and similarly we're going to let the limit as X approaches A from the right F of X, that's the limit as X approaches A of X restricted to X intersect numbers at least A X. And so what does this look like? So here's some axes. Here is our domain X. Here is our point A in X. And then let's say our function looks sort of like this. It's nice when up until the point A, and then suddenly we've got some kind of topologist sine wave madness going on. So in this case, let's call these points L, and then there's F of A, and then up here we don't even have a limit. So in this case here, the limit as X approaches A from the left of F of X is just that number L is this value. And the limit as X approaches A from the right F of X does not exist. And you can write out a precise definition, at least in the case where A is a limit point, of involving epsilons and deltas and things of the left hand and right hand limits. So if A is a limit point of our domain, x intersect minus infinity A, and that means that so A is the supremum of the points in X that are less than A. Then limit as X approaches A minus f of X equals L if for all epsilon greater than 0, there is a delta positive number delta such that if X is less than A and X minus A is less than delta, and you can write this as that's equivalent to X being between A minus delta and A, and also X is in our domain, and A being a limit point, A being the supremum of all these X values, it means there's is at least one X like this. Then f of X minus L is less than epsilon. And there's an exercise that's about coming up with a convergent sequence characterization of the left-hand and right-hand limits. Couple of things I wanted to say. First off, there's proposition 2.1.4 is that f, let's let X be a usual setup. X is a domain, A is in the closure of X, F is a function from X to the real numbers, and then F is continuous at A if and only if the two limits, the two one-sided limits, they have to both be equal to f of A. But if for some reason it's easier to check the two one-sided limits, then that's enough to verify continuity. And this, the proof is tricky because you've got some case analysis to do versus, isolated point on the left, limit point on the right, all that stuff. But from the picture, it's generally pretty straightforward. If it's a limit point on both sides, then it's continuous. If you're approaching your target point on both sides, if it's a limit point on one side, well, so it only really has to be continuous on that side. And so in either case, so remember we said you are continuous if your left hand and right hand limits are equal to each other, and they're also equal to the value of the function. So here's definition 2.1.6. Usual setup. Got a function from some domain on some domain and some point in the closure, and then if the two right-hand limits, if they are not equal to each other, if the right-hand limit and the left-hand limit are not equal but both exist, we say that F has a jump discontinuity at A, and if the two limits are equal, but they are not equal to f of A, that's what we call a removable discontinuity. I don't have time to prove this proposition in this video, and I do want to move on to derivatives in the next video, so I will just say that the last part of proposition 2.1.8, the part I didn't prove a couple videos ago, is that if f is monotonic, then there are several parts of proposition 2.1.8, but the new part is that every discontinuity, every point, that is every point in the domain where f is discontinuous, every discontinuity is a jump discontinuity.